Today's episode is with Will Huggins, a former football teammate of mine in high school and then at the University of Miami. Will is currently completing his master's degree in mechanical engineering at the University of Miami and is interning at Johnson & Johnson, focusing on 3D printing. Thank you for being here, and I hope you enjoy the episode. Will, what's up, man?
Hey, how's it going, Alan?
Just chilling, the usual.
Cool.
Spending summer, enjoying what's probably gonna be my last summer, at least for a while, because I'll start working.
Oh, really? Okay. What are you gonna work in?
Well, I'm not sure yet. I don't have like a specific place where I'm gonna start working in as soon as I'm done, but I'm gonna start looking for a job this upcoming semester. But yeah, I should find something for next January.
Okay, sweet. Sounds good.
Yeah.
I'm in the same boat. So,
So are you looking at maybe at the same place where you're interning right now, and then moving on from there? Like, do you want to stay in the same company, or do you want to look elsewhere?
well, I mean, I love Johnson & Johnson. It's been great working with them so far. As far as staying with them, that's definitely something I'm going to be looking into. But I know the field I want to work in is additive manufacturing. It's hard to predict the job market ahead of time. So I'm just going to be looking for the best offer.
Yeah. So what are you doing exactly right now? You texted me a little bit about it, but you could explain it a little more. It's not as simple as I guess it's a little complicated. Just give it a read.
Okay, yeah, no worries. So it's definitely not intuitive. I did not understand any of this when I was first starting out. I didn't even understand the field or know what additive manufacturing was before taking some classes on it and realizing how interesting it was. And now I've completely changed my career to orient around 3D printing. So additive manufacturing, AM, it is 3D printing. What I'm working on right now involves a few different type of technologies. So with my Johnson & Johnson internship, I am doing 3D printing of metals using powder bed fusion for applications in medical devices. I'm also interested in fat polymerization. So I'm working with a CLIP printer, which stands for continuous liquid interface production. And I'm doing my own project towards my master's degree, looking at applications for sports equipment. Also towards my master's degree and credit, I did a capstone project looking at paste extrusion applications of looking at how you can improve that technology by changing the amount of material supplied to the printer. So that is a lot. It is a lot of acronyms, and I wouldn't expect somebody who's not in depth in the field to really have that background. So I'm happy to explain a little bit more of the basics with that if you'd like, but
Yeah. Let's let's start with the 3D printing, the using metal for medical devices.
Okay,
That
totally.
sounds that sounds that sounds pretty interesting. I'm not fully sure what kind of things you can do with it. So if you want to talk about that a little more, I think that'd be pretty cool.
Okay, awesome. So when I first started out, I did not know the capabilities that this technology had. I am sure learning a ton, and it's awesome. So what I'm working on more specifically is powder bed fusion. Now, the way powder bed fusion works in AM with metals, you have a feedstock material. That's the material that you start out with, that's raw, that you're going to be building with. And in 3D printing, fundamentally, the entire science behind this manufacturing technology is that you build a part layer by layer, consecutively stacking layers on top of each other until you've completed your part. There's a little bit of mental gymnastics to get a visual representation of this. If you can imagine looking down on top of your part from a bird's eye view, a top view, every layer that's printed that is laid down one consecutive on top of the other is a cross-sectional view. It's a very, very thin layer. One way I might describe it is if you can imagine building a 50-foot tall Lego building contraption, any sort of item that you would build the first layer of Legos and then stack the second layer of Legos. And in 3D printing, it's essentially the same thing where you are making your flat cross-sectional view one layer at a time by depositing your material, your feedstock, on top of each other to build it up. In metal printing, you have powdered metal that you essentially weld together to make each of those layers and build up. In powder bed fusion, you have a platform with a very fine powder that's laid across in a thin layer. A laser shoots down into that powder. It melts the powder that it comes in contact with, which will then solidify. And that's how you make your first layer. You continue building up all the way until you're done.
So the powder bed fusion is the metal welding per se with the metal powder.
Yes, it's very, very small scale. So the one of the printers that I'm working with is powder around 45 microns. So a micron is 1 times 10 to the negative 6 meters. That would be 0.001 millimeter is 1 micron. So these are 0.045 millimeters at the largest per piece of powder. So they are very fine. It gives you great resolution. You can make parts that are very intricate, and applications toward the medical field are fantastic. So an example would be something customized. Johnson & Johnson has worked on implants. If you can imagine the process of a hip implant, hip implants are usually sized small, medium, large, and that's it. You kind of have to work with whatever size most closely fits the patient. With 3D printing, we can take scans of their body, and that patient can receive a hip implant that is made to perfectly fit their body at the exact dimensions in three-dimensional space, and it can be printed quickly, and it can be printed in simply just attaining a digital file. Other implants could include something for trauma. If you injure your brain will swell to heal itself. When that happens, doctors cut a hole in your skull so that your brain has room to swell without damaging itself. In order to seal that back up, you can use a metal, it looks a little bit like a mesh. It's thicker than a mesh, but you use a metal plate to seal that up. And we can 3D print those perfectly fitting the individual. That is some of the work Johnson & Johnson has done, for example, that's been used in people. So I think that's really interesting, and I've enjoyed working on it.
That sounds interesting. But that one of the things that comes to mind when you say that, it's difficult whenever somebody has some sort of injury and the surgery is performed, or some sort of replacement happens when surgery wise, like you said, a hip replacement, a knee replacement, whatever it may be. I feel like it's imperative and it is for the doctors to ensure that the body doesn't reject whatever part is being put in the body. How do you know? I know, I'm not sure if you're familiar with more so the medical aspect of it. I know you must be, you're more familiar with the engineering part of it, but do you know why or how those metal parts don't get rejected by the body? Like what do they do to ensure that that doesn't happen?
That is a fantastic question. And you're right that I don't have the in-depth medical perspective, but from an engineering point of view, really this comes down to material science. Now, what we are printing for implants and what Johnson & Johnson has printed for implants uses a titanium alloy. It's titanium 6 aluminum 4 vanadium. This is a medical grade material that the body is able to live with and accept, for lack of a better term. There are design characteristics that go into, say, a hip implant that you can change and alter to further increase viability. The details of which I won't really get into, but when you adjust both your solid model of the part as well as materials, the host can more easily accept what you're implanting when it comes to 3D printing.
Because it's adjusted to the exact measurements, you mean? Like to that person's measurements?
Yes, physiologically, the way the body will accept an implant, the way that the cells regrow, that the different structures in your body will heal themselves and grow back, you can mechanically adjust the model to be advantageous towards whatever part of the body will be working with this implant. So there are specific changes that can be made for each part that help out that process, whether you're talking about bone, whether you're talking about soft tissue. There are changes that can be made, which would make me go down and digress into a totally separate topic, which is bioprinting, which is the printing of live cells and being able to print human tissue. But that's a little bit outside of my field of expertise.
Yeah. Another thing that comes to mind is when it comes to like the degradation of the metal, you said you use a Johnson uses a titanium alloy, was it?
Yes,
For the
titanium,
parts?
aluminum, 4 vanadium.
Yeah, so when they use this metal, as the years go by, does it degrade? Does it oxidize? Like probably doesn't oxidize because it's probably, made to resist that kind of chemical reaction. But I mean, I'm sure it degrades at least somewhat from usage.
Great question. I don't have exact data off the top of my head to tell you. What I am aware of is that these implants will not need to be replaced. If done correctly,
Okay.
they are good to go.
For the patient's lifetime.
As far as I'm aware, yes.
That's interesting. I didn't know that.
Yeah. Yeah.
That's pretty cool.
You're printing things when you're installing a hip implant or when you're doing something for heck, even craniofacial implants. The objective is not to be forced as a care provider to put your patient into surgery, open them up, pull out the implant and replace it again. When you're working with these titanium implants, the goal would be to have it be a one and done situation.
Yeah. Yeah, I mean that's like I said, that's the goal. The less I guess the less frequent the patients have to go back to for whatever reason because they're having troubles, the better. So
Yeah,
if you can just
absolutely.
have it in there and not have it replaced, then that's the goal.
Yeah.
I want to talk a little more about the 3D printing thing because I think that's pretty interesting. I was listening to a podcast the other day or a couple weeks ago, um, where they were talking about, I think it was how they're starting to 3D print um like meat. So meat you can eat, right? But meat that is, I guess, um derived from exotic animals. So like tiger, for example, right? So since you can't really acquire tiger meat, they're producing it through 3D printing. I'm not sure how that works. I didn't even know that was possible. Do you know something about how like these different types of 3D printing are conducted and how it's done?
You know what? I hate to tell you, I don't know of any bioprinting tiger meat. What
It was
I'm
just a
aware
random
of,
example.
What I'm aware of within the field of bioprinting would not be considered consumable meat products. Bioprinting that I'm up to date on would involve printing a meniscus for, say, your knee. There have been some corneas that were bioprinted, as well as an ear and a nose. Other than that, I don't know of any that have actually been used for a patient. When
Yeah.
it comes to artificially making meat, what I'm aware of is that research is looking into doing this for beef, potentially chicken, so that one animal can be used to create a significant amount of portions by replicating that product. Although I don't know any specific details into how that is being produced.
Yeah. Yeah. It's just something I heard. I just don't know how it would be done, because I guess for each different type of 3D printing, you use a different material. So for example, with Johnson Johnson, you use metal, and then you have the regular 3D plastic printing that you see in most um art studios and stuff like that. And then I'm sure there's other materials you can use. I'm not aware as to what those are or how it's done. That's why I was asking. Maybe you did, but I'm not sure.
So, great question. There are 7 different technologies within 3D printing. Off the top of my head, you know what? I don't know if I can do it. We're live. I'm just going to try it. So there is extrusion based, there's sheet lamination, there's vat polymerization, there is powder bed fusion, there is electron beam melting, there is material jetting and binder jetting. There we go. I got it. Okay. So those are the 7 technologies used in 3D printing, and there are materials that are more advantageous for one versus the other. I'll point first to extrusion, which is what you mentioned. So FDM, fused deposition modeling, or FFF, fused filament fabrication. That is taking a plastic filament that you have the printer push the filament through a hot nozzle. It turns it into kind of a, how would I describe this? Maybe a goop, but it melts it down enough to where it can be pushed out, and it solidifies once it comes in contact with air again on the build platform. And that makes your simple plastic parts, and they're relatively inexpensive printers, a couple $100. And I say relatively inexpensive because there are printers that are over $1 million. But extrusion based is the sort of hobby horse printer. There's vat polymerization that works with resins and liquids, where you solidify the liquid, the resin, it's resin. You solidify the resin layer by layer, either with thermal curing or with light curing. That light is UV light. Or occasionally there's some research that uses our traditional white light for bioprinting. Again, I digress. When it comes to metal printing, you have powdered metals, and there are some fine resolution printers that can work with metals down to 5 microns. That's 0.005 millimeters diameter per piece of powder. We have sheet lamination, which is not a very popular technology. It's not widespread, not common, but it is where you have a large sheet of your material, let's say metal or paper, and you cut out what you don't want to create that, like I described earlier, that bird's eye view of the individual slice you stack on top of each other. And then you just cut your paper and you build in that way. You've seen almost Post-it notes, how they can be stacked in a spiral. If you can imagine cutting holes in each of those Post-it notes to make the middle a little bit more designed, you can create all sorts of features. And then there's bioprinting, which is live cells, and you can get into other things like paste extrusion, which would be printing liquids that come out of a nozzle and solidify, either again with heat or with your UV light. So the
What
amount of
what kind of
material,
what kind of like liquids, like what's the point of putting it, like using 3D printing for liquids? What can you make out of it?
oh, great question. Okay, so when you're using paste extrusion, one example within the research realm could be application towards energy storage. So having a material that reacts with an electric current, either it changes its temperature, or maybe when you impose a temperature on it, it develops that electric reaction, as well as physical deformation, where when you pump in a differential, when you pump in a voltage into that material, it may deform. And there are applications with that in medical. There are actually some applications in the space industry, in aerospace. If you're talking about resins, that would be vat polymerization, or DLP, digital light processing, or DLS, digital light synthesis. You can print parts with that resin that can be turned into functional prototypes. There are companies now which are printing medical equipment and athletic equipment. So as your viewers may or may not know, you and I played football at Miami together for several years, and before that at IMG. The shoes we were issued in 2020 from Adidas, the midsoles of those shoes are 3D printed by a company named Carbon out in California. And that was printed with resin, printing a type of polyurethane that they could create a very interesting design that wouldn't be possible with any other manufacturing technique.
So what kinds of liquids are used? So what actual liquid compound is put into these machines?
There's a wide variety. You can use a type of epoxy, which is a resin that, depending on which resin you're working with, could be thermally cured or UV cured. And when I say cure, that means it solidifies, it becomes hard, it's no longer gooey, no longer sticky, no longer flowing around. You can also add in, there's a University of Miami is interested in this field of research where you take a resin and you dope it with short fiber reinforcements. So there are a couple papers published from a professor at Miami looking at short fiber reinforcements with carbon fiber, with Kevlar. He may have published something with glass fiber as well, where you can now, using this resin with these short fibers, you can print materials that rival metals in their strength, which intuitively may not make sense, that you can just print some sort of epoxy and make it as strong as steel. Well,
It's probably lighter though, right? And it's like, I would guess that it's lighter, and it's like the kind of thing that the military would want to use.
it's lighter, it's cheaper.
Oh,
Yeah, it's very, very interesting stuff. It's still in the research phase. You're right that if the military has an application for it that they know of, they will be very interested in it.
yeah.
But as far as I'm aware, the paper that was published was in part related to the Air Force. And if I'm incorrect, then I apologize. But to my knowledge, there would potentially be aerospace applications with this material.
Yeah. I mean, I'm sure if it's cheaper and it's as durable as metal, then that's something that these fields would want to take interest in. Makes sense.
Yeah, definitely. So from what I read in the paper, the tensile strength is improved. If you're looking at a stress strain curve, now we're getting into a little bit of material science, but the tensile strength of this material was able to perform with, I don't remember the grade of steel. It was really threatening that level of strength. However, it does not show the same brittleness. It performed better, which I
Yeah.
thought was really interesting.
Yeah. That sounds interesting. So going back, you covered you have the regular like plastic 3D printing. You have the bio was it biotechnology?
Bioprinting. Bioprinting.
Bioprinting.
Right.
bioprinting. Then you have the metal printing, the liquid printing. I forget the specific technical terms for them.
No apologies, it's totally fine.
But you said there were seven. So what are the other three?
I see exactly what you're saying. Okay. When we're looking at these technologies, they don't all have their own special material.
Oh, okay. Got it.
There are more than one methods you can use to print metal powders. You can print metal powder with a binder jet or with the various types of sintering, either with powder bed fusion, laser sintering, electron beam melting. So the way I haven't talked about binder jetting at all. Binder jetting works where you don't have to melt your metal if you're printing metal powder. Instead, what you do is you extrude a binder. Think of it like glue. You put a layer of, so you have your metal powder already there. Instead of melting it to make your pattern, you put glue down in the pattern you want for your cross-sectional view, your slice. Then you put more powder and you put more glue, and you go in that order. And when it's done, the glue holding together will be the only thing that you're left with, including your metal. And now you've created your 3D part. So then you would just have to burn the glue off afterwards. When it comes to material jetting, you have ink that, if you can imagine like an HP office printer, something that you would print a piece of homework on. The way that works is that you have a cartridge of ink that slides across the width of the page and just disperses little dots of ink. The way material jetting works is that it does the same thing, but it can do so in a 3D capacity, and it can build up. I think it can get 16 separate materials at the same time, which is great when it comes to prototyping, because you can get different colors, you can get different textures, you can print very eye-pleasing prototypes with material jetting. Well, and then I think I already talked about sheet lamination. So that covers all seven.
Wait. We said six. You said the ink, the one that puts like the dots, right? What is it?
Yeah.
Ink spreading.
So
Was it
that material jetting,
material
just like an
jetting?
inkjet printer.
Yeah.
Conceptually, it's very similar.
Okay. So you talked about that one, and then you also talked about the glue, how it one of the what was it what was that called again? The one that uses glue?
Yeah, binder jetting.
Binder jetting. So you talked about binder jetting, and then you talked about the other one. Well, I think that's six. I think we're missing one, unless you already covered it and I got lost.
No, I'm sorry. I get excited. You know this. You've known me for years. When I get excited, I just ramble.
No, but it's good. It's good because like that's the whole point of like I'm not sure if I told you, but one of the reasons I kind of want to do this podcast is to invite people like yourself that are, I don't know, knowledgeable about certain thing, because then I get to learn about this. And usually if people are passionate about whatever it is that they're sharing, then it just makes it them much more interesting, because they convey it with a sense of emotion and intrigue, and then the other person also gets interested in it. So it's good that you're that way. It's not bad. Don't apologize.
Okay, thanks. I appreciate it. Yeah, it's a great idea, and it's certainly a field within podcasts that I know people enjoy listening to, because they have the same mindset that you do, and they want to hear from people that are passionate and that just so happen to be able to talk about what they're passionate about. So thanks for having me on. It's been great.
Yeah.
To answer your question, I believe sheet lamination is the one that we're missing. And
No, what you said, we said sheet lamination because that's when you said you can layer and build, like you put the example of a Lego tower.
Sure. Yeah. Okay. Lego tower works with,
So I don't think it was sheet lamination.
let's see, sheet lamination we did, binder jetting, material jetting. We did extrusion. We did vat polymerization. We did, oh brother, Um, we did the two metals.
So
Yeah.
we did all seven.
Yeah.
Okay. I might have got lost at some point. I
Oh,
thought
no
it was
worries.
six.
I know I clumped some together when they're similar. And I'm
But yeah, I mean but I'm sure, if they're similar, they can be, like you said, they can be put together sort of in the same category. So that's 100%. So those two you said are probably the two metals, right? You
yeah,
just mentioned.
yeah, you're right.
And the two metal ones are, which ones were they again?
Oh my goodness. You are really testing me today. So there is powder bed fusion, and I
Yeah.
believe the other one would technically be electron beam melting, but just to
Okay.
make sure I get the right answer, I'm going to Google this.
Yeah, because I don't
The reason
remember.
why is I've got them right, but I want to make sure I give people the exact wording.
Yeah.
Okay, it is not electron beam melting, it's directed energy deposition. I
Okay.
don't know how I forgot that.
It's
Okay,
fine.
great. So let me tell you quickly, directed energy deposition. It is also metals. Instead of using powder, okay, I'm just going to restart. Instead of using a bed of powder, directed energy deposition has a laser that fires. And on either side of the laser are these little ejection tubes that shoot powder into the laser beam path. And they, while in contact with the laser, will melt. They get shot down to the location the laser is pointing, and then it solidifies. It's like welding within the laser's path. This is a great technology when it comes to repairing a material. If you just have a little chunk taken out of something, that you can fill it back in with that metal. And it's a very expensive technology. It's one of the few that Miami does not have on campus. Miami's, by the way, is a great additive manufacturing school within the College of Engineering. I've learned a ton, and I'm really happy about it, excited about it. But
That's cool.
directed,
I can't, I don't know if I should comment on my side of things. I don't know if I could say the same about the business school, but
oh, come on. The Herbert
yeah,
Business School is great. They've got a ton of funding. They just got this brand new
or at
facility.
least the undergraduate part. I
Oh,
don't know.
come on. Don't give them a hard
No
time.
comment. No comment there.
Oh, brother.
But
Oh,
you were saying about the that technology, how it's expensive and it's good for manufacturing,
yeah, it's
repairing.
great for repairing parts. That I think is the thing that stands out to me the most. If you have a 3D printed piece of metal and it breaks, you could potentially fix it with directed energy deposition. And to me, that's really cool. In other, I'm trying to think of, quite honestly, in the other AM technologies, direct energy deposition is obviously the best at fixing a part. I think you'd really be pressing your luck if you try and do that with any form of extrusion. I guess it could be possible, but in the other technologies, it really doesn't make a lot of sense to try and repair a broken piece that chipped off. Or so when you have a metal part and you have direct energy deposition that will work for it, that's great. So anyway, the 7 technologies would be direct energy deposition, your powder bed fusion, your extrusion, vat polymerization, material jetting, and binder jetting. So there you go.
Yeah. Yeah. Is 3D printing the project you're working on right now, aside from your internship?
Yes. So for my graduate credit, I am currently working on 2 individual projects, and they involve vat polymerization as well as extrusion. So I'm working, well, I just wrapped it up actually. I was working on a project with paste extrusion, which is similar to FDM, only instead of printing plastics, you're printing paste. And the project involved extending the feedstock supply from very limited attached to the print head onto an external vat that, if you were able to replenish it, you could in theory have an endless feedstock supply. So that was the project I worked on with paste extrusion, and I'm working on a clip project, continuous liquid interface production. It's a form of digital light processing and vat polymerization. I want to prototype athletic equipment with our football backgrounds. Intuitively, you may be able to imagine ways in which having something customized that could work as a shock absorber that's made of materials that are strong yet have some elasticity to them. You can see how that may be useful. So as you know, the Rydell helmet is made with clip so that when you go in with the, oh my gosh, what are they called? The Diamond Fit, the Diamond series. The Rydell helmets where you see the player's name signed in the back of them, those were done with 3D scans of their head, fed into a computer software that can then 3D print the pads of the football helmet around their head. I already mentioned the Adidas 4D shoes, the midsoles, the cushion on the outside is completely 3D printed. And other companies are printing things like bike seats, pads for boxing gloves. A new pad for a backpack that filters air has been launched. And these are things on the market that are full scale production being sold, which is fantastic for 3D printing. That's been one of the shortcomings of the field in the past, where the material and the printed product are in question for their durability, their strength, their reliability if they were going to be used on something like an airplane where people's lives would depend on it. But the field is definitely pointed in the right direction. And at this time, especially with metal printing, I think really one of the only limitations is the cost. Once we get the cost down, this form of manufacturing will completely take over the field of manufacturing as a whole, which will be very exciting.
Yeah, this whole market of 3D printing is definitely something that is on the rise and will continue to be on the rise just because of how many applications it has in the real world. So I'm 100% with you on that.
Yeah.
I know that you have to go here soon.
Yeah, unfortunately, I do. It's been great talking with you. I hope I've provided something interesting and that people listening have enjoyed. I certainly have. So thank you very much for having me.
Definitely. And there's still a lot more things we can cover in the future. You can anytime, man, if you want to come on again. Like I said, I mean, it wasn't a long time, and there's plenty more that I know you would probably like to talk about, and I would like to listen. So if you ever want to come on again, that'd be awesome.
Heck yeah, sure thing. Totally.
All right. But for now, thank you, Will, and thank you for making time out of your busy day.
Yeah, totally. Thanks, Alan. Thanks for having me, and I'll see you around.
Yeah. Thank you, everyone.